There are two ways to monitor the rate of a reaction. Once you've decided which product or reactant you're going to monitor and keep track of, you have two different ways to go about keeping track of that reactant or product. And one of them is monitoring by color, and the other is monitoring by pressure. If you want to monitor by color, then you have to have something in the reaction that is colored. And ideally, only one thing that's colored. One example of a reaction that would be easy to monitor by color is the reaction between bromine and HCOOH. And they produce bromide ions, hydrogen ions, and CO2 gas. And this reaction is really great to monitor by color because the bromine in this reaction is red, and all the other things in this reaction are colorless. Which means that as this reaction proceeds, and as bromine is consumed, the concentration of the bromine decreases, and the red color goes away. It's really easy to monitor this with like a UV vis. You can just do the reaction inside the UV vis and watch the intensity of the color as it fades. The intensity of the color is directly related to the concentration of the bromine with equations that you learned in 161. And so you could do the reaction inside the spectrometer, collect a bunch of data, and make a graph of the decrease in the concentration of the bromine over a period of time, and it would probably look something like that. And then you could calculate the rate of this reaction with your data. Because this is a reactant that we're monitoring, bromine, it's a negative rate, it's a negative change in concentration for the bromine per change in time. And it would be measured by taking the final concentration of the bromine and subtracting from it the initial concentration of the bromine and dividing that by the total amount of time that passed, final time minus the initial time, which is probably 0. This, if you do this math, you're actually measuring, really just comparing the concentration here at this time and the concentration over here at this time, and you're taking the difference between those two. So what you're actually going to be measuring is calculating with this equation is data that looks like that. You're just taking two data points and then fitting them together, which is not great. And so the rate that you get from this equation is not really the rate of the reaction, it's the average rate for the whole entire. This is the average rate. It's the average rate for the whole entire reaction from beginning to end, and it's kind of limited in terms of its usefulness because it doesn't really tell us what's happening at like this time right here. I mean, if we look at if we were to plug in this time into our the calculations that we do down here, we'd get way incorrect value for the concentration of the bromine. So it's really limited in terms of its usefulness. The actual rate of a reaction, it shouldn't be averaged out the way we do it with this equation because it's not a constant. It varies with time. For this reaction that I've drawn here, you can see the rate is really fast at first, like the concentration drops really quickly, and then the rate slows down. So the average rate is pretty limited in terms of its usefulness. Because the rate is related to concentration, and not just something that we can average out, we need to come up with a more valuable equation than the average rate equation that we use here. So, using our generic A goes to B reaction again, we're going to say that the rate is not just the change in concentration per time, but that it's something that is directly proportional to the concentration of, let's just say A, but it could be B, doesn't really matter. If we want to turn this proportionality into an equality, all we have to do is add a constant. And then, ta-da, we have an actual equation. And the constant that, or the letter that we choose to use for our constant in these kinetics equations is a lowercase k. K is called the rate constant. And it depends on the reaction. So each reaction has its own k value. And it also depends on temperature, because as you know, if a reaction is exothermic or endothermic, the temperature does have an effect on how quickly the reaction proceeds. And it's not something that you can calculate. It is experimentally determined. And one of the things you're going to do in lab is determine the value of K experimentally. You are going to determine the value of K for a reaction in lab. And because of the format of this equation, rate equals Ka, we can, the way that you determine the value of K is by plotting the rate of the reaction per concentration. So you do the reaction multiple times with multiple different concentrations of A, and you get multiple rates, and you plot them, and you end up with something nice and linear, and the slope of this line is K. It seems very easy, and it is.